All right, so we have discussed algorithms and looked at some examples of algorithms, and we are working towards a discussion of algorithmic complexity, which is essentially like a way to sort of measure how complicated an algorithm is and how long it would take to complete. But on the way there, we need to discuss the growth of functions. So we're going to be using functions to measure algorithms, and what we want to do is basically establish a way of classifying functions by their growth rate, sort of. I want to begin this discussion with a graph. I'm just going to go over a graph here, and I'm gonna show you a bunch of different familiar functions, and these are going to be a set of functions that we're going to come back to over and over again, because these are the functions that we generally use in computer science to measure the growth of algorithms. So right now, we're just going to think about these as functions of some input n. You can define things with an input x or with an input n. And generally, if you're talking about a continuous function, you use x as your input because it's any real number. But if you're talking about like a function where the input has to be an integer, then you use n. I'm going to kind of go back and forth between these two. In section 3.2, you'll see a lot of the use of x as the variable, but then in section 3.3, when we get to talking about algorithms, the input is assumed to be an integer, so then we'll start calling it n more often. I want you to be comfortable with either one. They really are the same. It's just a matter of what type of input you're talking about, real or integer. So I want to go over some different functions that have different growth rates initially before we get into the nitty-gritty details. But first thing I want to say, actually, just preface this entire chapter, really, it's 3.2 and 3.3, is that I don't really consider myself an expert on these things. I've just sort of learned this stuff pretty recently, and I'm presenting it to you. I'll present it as best as I can, but please forgive me if I make any mistakes. I do want to mention I reached out to a friend and former discrete math student, Andrew Haas, in Michigan. And he helped me a lot with these lessons, the preparation of these lessons, and just kind of to help me understand these topics a little better. So shout out to Andrew. Thank you, my dude. So let's begin. So of these functions, the one that has the lowest growth rate is a constant function. So the first thing I'm going to do here is plot in red my constant functions. There's my constant function. Let's call that 1. Okay, 1, like y equals 1, is a function that doesn't grow at all. So that's the slowest growth you can have is no growth at all. So the next slowest type of growth, okay, next after that, would be a logarithm function. Logarithm functions grow pretty darn slowly. So I'm going to plot logarithm here, log of n, in orange here. So that's log of n right there. It looks like that. Generally, yeah, no, never mind. Log of n is a function which looks sort of like it might have a horizontal asymptote, but it doesn't. Remember, you may remember thinking back to college algebra. This is a function that is going to increase forever, but the rate of increase is going to decrease as it increases. So it's increasing forever, but it's slowing down significantly. All right. So that's a log of n function. Now after that we have y equals x, the n itself. So f of n equals n, which is it's not a constant function, it's a linear growth function. Sorry, I almost misspoke there. I'm going to plot that here in green. So that's n. So this would be where the output is just equal to the input. Okay, so we have n is sort of like a nice benchmark, right? N, like f of n equals n, is a nice familiar idea. 1 is a nice benchmark because it's constant. Log of n lies between them, right? So it's slower than n, but it's faster than 1. So that's what we have so far. Now, a function that grows faster than n, one example is n squared. N squared grows faster than n, so I'm going to plot n squared right here. N squared is this function. Hang on a second, let me get this right. It is this one. right here. Yep, that's n squared. Comes up to here, n squared. And n squared definitely grows faster than n, right? N is a straight line, n squared is a parabola. But there's another function in between these two. So between green and blue, I'm going to put psi n here. And the function that's kind of in between these two, it kind of comes from the fact that between 1 and n we have log n. And that is this function here, which is n times log n. So n times n would give us n squared. N times log n gives us something which is bigger than n, but less than n squared. So you can kind of see the parallel here, you know. And in your homework, you will actually be proving that that n log n grows slower than n squared by using the known fact that was established in the section that log n grows slower than n. So yeah, there's that. Now there's a couple of types of growth that are even faster than n squared. So the next one faster than n squared you may be familiar with would be an exponential growth. So I'm going to skip some here. But faster than n squared, you have n cubed and n to the fourth and n to the fifth. Those power functions are growing faster than n squared. But even faster than all of those is exponential growth. So exponential growth I'm going to put in purple here. So exponential growth, oof. I'm going to write 2 to the n. 2 to the n is a type of exponential growth that is faster than n squared. Any exponential growth is going to be faster than any polynomial growth. But there are every different possible exponential function with different base, it grows at different rates. So like 3 to the n would grow faster than 2 to the n because 3 is bigger than 2, and so on. So we're really only going to consider bases for exponential functions that are like bigger than 1. Because we're primarily concerned with growth, not decay. But there's one more function left on here that I haven't drawn yet. So there's one type of function that grows even faster than exponential, and that is factorial growth. So we used factorial when we were counting things in chapter 6. So I'm going to show you what factorial growth. Factorial growth, n factorial kind of dips down here at the beginning, but then it comes up and it gets super, super fast. And so n factorial is our fastest growth. So that's just some examples there of different functions that are going to grow at different rates. And we're going to use these as our like benchmarks and to compare things and to think about things. So now, how do we actually define this idea of growth? Well, it turns out it's not just a matter of, less or greater. It's not just a matter of like which function values are less and which function values are greater. It's actually a bit more complicated than that, because you could say n squared and 5n squared, or n squared and n squared plus 2, and all of those functions actually grow at like approximately the same rate. They're all sort of analogous to one another. One of them might be a multiple of the other, or one of them might be like a shift of the other, but all those different parabolas, they all have the same growth rate. We want to classify them together. And so we have a definition, there's something called big O, which is a way of kind of putting a bound on the growth of something. And I'm going to define it a little bit differently than the textbook defines it. So I got this from Andrew. He introduced me to this definition, which I like. And this definition is equivalent to the one in the textbook, but it just uses slightly different notation. It introduces big O of a function. So this is the big O. It's actually a big capital Greek letter omicron, which is like a Greek O, but we can just call it big O. Big O of g of x, where g of x is some function, is actually defined as a set of functions. Basically, it's the set of all functions that grow up to as fast as g. So anything that grows slower or as fast as g. And it's defined like this: a set of all functions f of x such that there exist two real numbers, capital C and k. So we have c and k, which are both reals. Then we need these two numbers, and those are going to be thought of as like constants that satisfy, that satisfy this, that the absolute value of f of x is less than or equal to this multiple c times the absolute value of g of x for all x values greater than a certain amount. Okay, and the c and the k are called witnesses. So in this situation, like for example, 1, let's just do a quick example here. 1 would be an element of big O of log of n. And the way we can tell is because 1 is less than or equal to 1 times log of n. 1 is less than or equal to log of n, but not necessarily all the time, right? Like log of n is actually smaller right here at the beginning. You can see the orange line is actually beneath the red line initially because it starts down here at 0. So when does it cross over 1? Well, it's when, this is usually considered to be log base 2, by the way. For computer science, we do most things base 2. So let me just introduce that here. Sorry, I forgot to mention that earlier. Let's see, log base 2 of n, log base 2 of 2 equals 1, right? So really the place where they cross right here is when n equals 2. So this is as long as n is greater than or equal to 2. So what we have here is a situation where our witnesses are the values c equals 1, because I didn't put any multiple here. 1 is less than or equal to 1 times log base 2 of n, so my c multiple is just 1 itself, and k is equal to 2. So k is like the, here, k is 2 on here. K is the sort of x or n value after which this inequality is going to hold. It doesn't matter what happens earlier on, because we're only like concerned about overall growth, like long-term end behavior, basically. So if there's some period of time early on where the inequality is not true, that doesn't matter. Okay, it just has to be like eventually true. This is called the tail end of the function. So after a certain point, it becomes always true that f is less than g, or in this case, 1 is less than log n. Okay, so that's just a quick example. We'll do more examples soon. So a couple notes on notation. So with this definition, where big O of a function is defined as a set of functions that are like slower or equal in rate, we would say f of x is an element of big O of g of x, right? That's how you say that. But you'll also sometimes see people write f of x is or equals big O of g of x. So you could write it that way, or you could write f of x is big O of g of x. And this last version is actually the one that the textbook uses. Okay. It introduces the notation, or like the language, f of x is big O of g of x. And that's fine. But all of these are valid ways to say it. You can either say equals big O of g of x or is an element of big O of g of x. I mean, technically equals and is an element of mean totally different things, but they are both used sometimes to mean the same idea. Okay, so it's a bit of what we call an abuse of notation, where we're kind of using different notations to mean the same idea, but they are technically different notations, and they should mean something different, but we're just kind of, as long as we know what we're talking about, then we're good. Okay, so you'll see any of these. All right, so one thing I want to point out about these examples here is that if we're using the set notation, the big O of these functions are all going to be subsets of each other. So like, let's do the colors again, just to color code stuff. Big O of 1, this would represent the set of all functions that grow no faster than 1. So this is not necessarily just going to include constant functions. It would include a bunch of constant functions, but it could also include things like a sine function or a cosine function, because they have an upper bound, like sine and cosine. Here, sine and cosine wobble around like this, right? And you can, even no matter how big sine or cosine is, even if it's like 2 sine or cosine or 10 times sine or cosine, you could still put a constant up here, y equals c times 1. And also down here, y equals c times negative 1. And you could say that the absolute value of this sine function, like say this is sine of, or like y equals like 10 times sine of x, some large multiple of sine. It's with a big amplitude. You could still say that that's going to be big O of 1, because it is always going to be less than a multiple of 1, right? So you can put like a upper bound and a lower bound on that function that are proportional to 1. Okay, so that's what it means for something to be big O. So big O of 1 is going to be a set containing all constant functions, as well as anything that has like a upper and a lower bound, like a sine or a cosine. So then that will be a subset of the set big O of log of n, right? Because anything which is big O of log n grows no faster than log n, therefore it's definitely going to grow no faster than 1 as well, right? So anything which is in big O of log n is going to be in big O of 1. And that in turn will be a subset of big O of n, right? Because anything growing no faster than n will definitely also, hang on, have I made a mistake here? Are these backwards? No, I haven't made a mistake, but I was saying it wrong just now. Anything which grows no faster than log n is definitely going to grow no faster than n, right? So anything that's like less, growing slower than log n is definitely going to be growing slower than n as well. These are subsets, and these really could be written as proper subsets rather than just regular subsets, because there's definitely going to be things that are big O of n that are not big O of log n. Right? So there's things in here that aren't in here, right? So like any linear function. It turns out any linear function is going to be in here. They all grow at the same rate. But those aren't necessarily going to be this slow, right? And so on. So this sort of containment goes on and on and on and on. So anything that you can say that is, anything that you can say, any function that is big O of n squared, for example, is guaranteed to also be big O of 2 to the n, and big O of n factorial. Okay, but not vice versa. So something which is big O of n factorial might not be big O of n squared if it grows at the same rate as n factorial, for example. Okay, so that's sort of an introduction to the definition, the notation, and sort of the concepts. Now I'm going to do some more examples to kind of clarify some of this.